Determine the wavelength of sound using stationary waves. Question 1. Describe the method. Question 2. Some specific questions. A. For the arrangement shown in Figure 15.17, suggest why it is easier to determine accurately the position of a load rather than an antinode. B. Explain why it is better to measure the distance across several loads. Question 3. To work out an example of experimental data processing. For sound waves of frequency 25,000 Hz, it is found that two nodes are separated by 20 centimeters, with 3 antinodes between them. A. Determine the wavelength of these sound waves. B. Use the wave equation V equals to F lambda to determine the speed of sound in air. The method of this experiment is illustrated by this figure. The loudspeaker produces sound waves, which are reflected back from this vertical reflecting board. So a stationary wave will be produced. In the space between the loudspeaker and the board, which can be detected by the microphone here. And the microphone is connected to the oscilloscope, and the time base of the oscilloscope is turned off. So what we can see on the screen of the oscilloscope is just a spot moving up and down. The vertical height of the trace of the spot gives a measurement of the amplitude of the sound wave detected by the microphone. So by moving the microphone along the line between the speaker and the board, we can determine the position of loads and antinodes of this stationary wave. Then measure the distance between these positions. We can get the wavelength of the sound wave. To specify this, let's move on to look at this figure. This is a stationary wave. As we can see, the separation between two adjacent antinodes is half of a wavelength. So is the separation of two adjacent nodes. So the wavelength is 2 times the separation. If we measure distance across several nodes, the wavelength can be calculated by this equation. Wavelength equals to 2 times the distance across several nodes divided by the numbers of the nodes minus 1. Now let's answer 2 specific questions. First, why it is easier to determine accurately the position of a load rather than an antinode? Because the amplitude of oscillation of loads are 0. So if the microphone is placed at the position of a load, what we'll see on the screen is just a spot staying at its original point on the center of the screen. Just stay there, no moving. And if you move the microphone a little bit away, you'll see the spot starts moving up and down. So it's very convenient to accurately determine the position of a load. However, the amplitude of antinodes is at their maximum. So the spot will moving up and down to a maximum height. And if the microphone is moved slightly away from the position of an antinode, the spot on the screen will still move up and down to a big enough height. So it's not easy to determine the position of antinodes. So that's the answer For question A, hopefully it will make sense to you. Now let's move on to the question B. Explain why it is better to measure the distance across several nodes, not just two nodes. This is simple. That's because measuring a longer distance produces a smaller relative error of measurement. That's what we always do in experiments to reduce measurement error. We always measure the total amount of many units, then divide it by the numbers of units to get the average value of every unit. So that's for the question B. Let's move on to the next question. To work out an example, they give us the frequency of the sound wave and the distance 20 centimeters between two nodes with 3 antinodes between them. So we can draw a figure. Two nodes with 1, 2, 3 antinodes between them. So there are 1, 2, 3 separation, and each separation is equal to half of a wavelength. So we get 3 times half wavelength equals to 20 centimeters. Then get lambda, which is the wavelength, equals to 30.33 centimeters. That's for the question A. And the question B is asking us to determine the speed of sound. And the speed of the sound V is equal to F times lambda. F, the frequency is 25,000 Hz. And the lambda we have just worked out, which is 13.33. Convert the units centimeters into meters, divided by 100. So we get 333.3 meters per second.